Thanks for the introduction. And good afternoon, everybody. My name is Lei Yang from Tsinghua University. It's my honor to present our recent work, See-through walls with COTS RFID systems. The co-author Qiongzhen Lin and Tianci Liu are the third-year PhD students, and Professor Yunhao Liu from Tsinghua University, Xiangyang Li from the IIT USA. This is my talk outline today. See-through wall and passive tracking technology has been widely studied in recent years. Many applications would benefit from this technology. For example, it can improve the game experience and the jet control. It also help the editor surveillance or detect the intruder. Mentioned the see-through technology, our first response is the radar. Indeed, the radar, it has been studied for many years in the radar community. However, the radar occupies a wide frequency band, which may impose the interference on other device. And the radar is not always accessible to the surveillance in most of the world. We searched the see-through product in Alibaba. We found that a 100 Ranger cost about $4,500 per set, and the rescue tool cost about $90 per set. Is very expensive. And recently, our community also exploits the same technology used Wi-Fi. For example, the Y-Wave and Y-Track from MIT. This method requires the customer device, like the USRP or the WAP. And they also need the device to emit the customer signal, for example, the FCFW. In this work, we are trying to exploit the same technology using a commercial device with the legal frequency band and being accessible to the surveillance purpose. We turn our attention to a major technology, RFID. RFID is evolving as a major in the technology enabler for the identifying and the tracking around the world. In this work, we used a purely commercial RFID device to implement a see-through wall system called the Tadar. When I asked the question, can we use the RFID system to enable us to track objects through walls? Almost anybody answers absolutely no. That's true, because in the RFID system, the tag modulates its ID using a backscatter signal. Such a signal is too weak to pass through a hand, not mention a wall. Let's review the RFID system. It's well known that the RFID system adopts a symmetric architecture, which has three important features. The first, the RFID provides a strong transmit signal, which is sufficient for the two-way transfer through a wall. The tag modulates its ID using the backscatter signal, and H is vulnerable to the ambient reflections. And more importantly, the RFID system comes from the radar. So the radar is good at resolving the weak signals from the background. Inspired by these three features, we redefined the RFID system to extend our scenes. First, we leave the radar to supply the RFID signals to light up the object in the room. Second, we attach a group of tags on the outer wall and treat them as the antenna array to receive the reflections from our target. Apart from the tags, the signal also reflects by our target. These reflections, as well as the signal from the radar, combined at the tag. And the tag uses this combined signal to modulate ID. As a result, the backscatter signal received by the radar implicitly contains the reflections from our target. If we would somehow can somehow separate the reflection from the backscatter signal, we would to be locate our target. Let me show the current state of our research. I'm going to play a short video show that our tracking results. We deploy the tag array and the radar antenna behind the wall, and we use a robot taking a notebook as the reflector. The red point is the output of our tracking systems. Reader is compact, low cost, and accessible to the surveillance purpose. The rest of this talk, I'm going to address the following challenges. The first challenge is quite challenging to separate a weak signal from another weak signal. Especially, this task must be accomplished using a commercial device. It means that we cannot make any modification or the access to the low-level layer, the physical layer. Due to the flash effect, the reflections from our target will be joined in the reflections from the surrounding static objects, and we also face various hardware diversities. To better understand how the reflection affects our back scanner, we conduct a group of empirical studies. Due to time limitation, I organize the details. If you have interest in, you can refer to our paper. Here, I only present our conclusions. The first conclusion we found is that we found there exist 3 dominant propagation paths among the radar A, tag T, and reflect X. The first path is from the radar A to the tag T. The second path is from the radar A to the reflect X and then to the tag T. The third path is from the tag and to the radar. The second conclusion, we find that the signals propagating from the first 2 passes combined at the tag, and the tag uses combined signal to modulate the ID and send back it to the radar. So, thus, the backscatter signal received by the radar, in fact, implicitly contains the reflections from our target. If we find a way to separate each, we have the opportunity to locate our target. The key question is how to separate the reflections from our backscatter signals. We address this issue from 3 cases. In the first case, the signal between the radar and the tag propagates through the line of the set without any reflections. This figure shows the first case, the signal emitted from radar and backscattered by the tag. This equation shows the backscattered signal, or model the backscattered signals collected in the first case, in which the SA to T is the signal received by the tag, and the ST to A is the backscatter signal collected by the radar. In the second case, we attach the tags on the outer wall and keep the room empty. In other words, there is no target moves in the room. In this case, besides the tag, the other surrounding static objects like the walls, furniture, chairs are also reflect the signals. In this equation, we call the reflections from a static object as a flash. In our equation, we treat the flash as if they were emitted from a virtual single point, W. In this way, you can see that the radar will receive the 2 kinds of the signals. One is from the radar, and another is from the point W. In the third case, we consider scenario in which our target moves in the room. Due to the existence of the object X, an additional signal is reflected to the tag. The signal is the SA to X to T, and the backscatter signal is revised using this equation. To derive the reflections, we use the backscatter signal collected in the third case to subtract the backscatter signal collected in the second case, and then divide it to the backscatter collected in the first case. We can see that the reflections from the surrounding static objects and the signal from the radar are totally removed by the subtraction. And lastly, we have this simplest equation. Let me zoom in to see what is the SA to X to T. H is the reflection signal, and H can be modeled like using this equation. This equation seems a little complicated, but don't worry about it, because most of the variables we will handle later. Here we only care about two variables. The first variable is H, A to X to T. H denotes the parameter of the channel from the A to X to T, namely our reflection. The H is the only variable related to the object's location, so of course it's our goal. If we can resolve this term, we can locate our target. The second term is Hx. H denotes the reflection activities of the object. You know that different objects takes different impact on the reflection. It totally depends on the object materials. We use Hx to denote this characteristic. Then we substitute the reflection equation into our derivation. We can something amazing happens, that most of the unknown variables related to our hardware diversities are totally removed from the subtraction or from the division. And last, we have this simplifies the equation. After transforming, we have this equation, and let's review the items in this equation. The HA to X to T is the channel of the reflection, of course, is our goal. And the STWX to A is the signal, is a backscatter signal collected in the third case. And the STW to A is a backscatter collected in the second case. And the ST to A is a backscatter signal collected in the fourth case. The HA to T is the parameter of the channel from the A to T. Since both the reader's location and the text location are known in advance, so this item is calculable. And the last item, as we mentioned, it denotes the reflectivities. H is unknown. However, it is a constant. It's easy to remove the constant from the equation, use some mathematical trick, and I will introduce how to do it later. Based on this equation, we can see that it's amazing that Tadar is independent on all the unknown variables related to the hardware diversities. Which means that we don't need to care about which and what device you are using, and we also don't need a calibration phase in advance. It's more amazing that Tadar is independent on the transmitted signal from the radar. Which means that we don't need care about the radar's implementation details in the physical layer. Now we put all the pieces together, sketching our algorithm as follows. Our algorithm contains 3 steps. In the first step, we learn the backscatter signal while keeping the LOS propagation and reflected free. In second case, we learn the backscatter signal after attaching text on the wall and keeping room empty. In the third step, we derive the reflections when the object moves in the room. Now I will show a short video to see the separated reflections. In the figure, the yellow lines shows the amplitude of the separated reflections. We can see that as the distance increased, the amplitude decreased. Our next task is how to use this separated reflection to track our target. Here we adopt the scattering model. We assume that the signal emitted from the radar will be scattered to anywhere. It means that the reflections will be received by multiple tags. Then we use a hidden Markov model to model the object motion. We treat the object's location as the hidden states and treat the separated reflections as the observations. We think the system performs a transition after the object moves from one location to another. In order to remove the impact of the reflectivities, we choose one tag as a reference and use other tags backscatter signals to subtract that of the reference. We implemented the whole system using the COTS device. We use the impinging reader and the alien tags. We attach the tags on a plastic box instead of wall to maintain their geometry relationships and locations so that we can move it anywhere. And to traverse a concrete wall, we adopt a high-gain direction antenna. One key functionality of the radar is to separate the reflections from the backscatter signals while eliminating the hardware diversities. We use the grids to show the amplitude of the backscatter signals collected from the tags. Each grid corresponds to a tag, and its grid value denotes the amplitude. This figure shows the case that there is no any reflector in front of the tag array. We can say that the amplitude distributes out of the order. Then we place an iPhone in front of the tag array. We can see that almost all the tags becomes lighter because of the reflections. And it validates our assumption that the reflections will be received by multiple tags. However, the amplitude distribution is still out of the order. The third figure we shows the amplitude distribution of the separated reflections. We can see that the distribution is in the order as we expected, and the central grid becomes the brightest because it is collected from the tag which is closest to our smartphone. This experiment shows that Tadar well eliminates the impact from the unknown hardware diversities. Next, let's see how the Tadar performs as a function of the material of the building. We can, from the figure, we can detect the furthest detect the mobile object at 8 meters in free space. However, the range drops to 3 meters. This is expected because the concrete wall is thinner and much harder to pass through. Therefore, the signal is weakened a lot after it travels twice. We also present the tracking accuracy of the Tadar and compared with its other existing non-UWP method. We find that tag can achieve about 80 centimeters along the X dimension and the 20 centimeters along the Y dimension. Tadar makes a contribution by enabling device-free mobile object tracking. However, it still has some limitations that left for our future work. For example, since both the radar and the tags are directional, so our system is directional dependent. It means that our current protocol distributes tag in a fairly large area to enable them to receive the reflections from different perspectives. And second, we need to learn the environment in advance. However, in most of the time, maybe this is not the case. And we can only track a single object currently. In conclusion, in this work, we proposed a low-cost solution to the through-wall tracking of moving objects, enabling the surveillance purpose. And we found a way to separate the reflections from the backscatter signals. And we also demonstrate a working system implemented purely based on the COTS RFID device. That's all. Thank you for your patience.